Thank you, Nila. And thank you to the organizers for inviting me for the conference, for the workshop. So today I'm going to talk about a more general class of quantum relative entropies called quasi-relative entropy, but I'm not going to be actually talking about that much general class. It's called f-divergence, a little bit smaller. And I will talk about the Pinsker and the reverse Pinsker inequalities for this relative entropy. And in particular, you can derive the reverse Pinsker inequality for Tsallis entropy and for the relative entropy. And at the end, I will talk about the closest separable state, which of course is how you can measure the entanglement in the system. Okay, so we've seen quantum relative entropy a couple of times before in the conference, and we'll see it again today and later. So it's a sort of like a measure of difference between two states, rho and sigma, and it's a function of these two density matrices as a trace rho log rho minus rho log sigma. And it has several interesting properties. Well, first of all, it's non-negative, and that's how we expect a measure to be. It also can be infinity when these states are sort of like orthogonal to each other. So the larger the relative entropy is, the easier it is to distinguish these two states. And the closer to zero they are, of course, it gets harder and harder. And the relative entropy satisfies many properties that we expect from the measure right away. For example, it's invariant under unitary operations. And that means that if you have two states, rho and sigma, you do something locally to both of these states, to both of the states, and that should not change the way you can distinguish them. It's also additive in a tensor product. And one of the most important properties is the data processing inequality. We've seen this inequality yesterday for for one of the generalizations of quantum relative entropy, and we're going to see it today later in the talk of Mark Wilde. So here N I denoted as a completely positive trace preserving map, which is a quantum channel, and in particular it holds for partial traces. So if you have a state rho on two systems, A and B, and sigma on two states, once they pass through the noisy quantum channel, it gets harder to distinguish them because the information gets scrambled, so to speak, and the states become closer to each other in a way that they're more and more scrambled. There are several interesting equivalent statements that relate to entropy and the relative entropy. So for the entropy, there is a strong subadditivity inequality. There is also joint convexity property of quantum relative entropy. So if both states can be written as a convex combination with the same coefficients, probability coefficients Pj, then the relative entropy is jointly convex. And there are two statements about monotonicity. What is interesting is that all of these statements are equivalent to each other in a way that if the monotonicity under partial, let's say, traces holds for all states, then the strong subadditivity of the entropy also holds for all states. The interesting result, of course, is how do you go back from the partial trace to the general quantum channel? I mean, the partial trace is a partial case of a quantum channel, but how do you go back? And the way you go back is through the Stein-Spreen factorization theorem that says that any completely positive trace preserving map can be viewed as a partial trace on a larger system. So you take your system, tensor it with an identity on a larger system, make the unitary evolution, and your quantum channel is a partial trace of that unitary evolution of a larger system. So after the unitary evolution, that's your state on two systems, A and E, and the quantum channel, that's just a partial trace of that. But you can see more about these statements and how one is derived from another in the Wikipedia article titled Strong Subadditivity of Quantum Entropy, which was written by Elliot Lieb, Eric Carlin, and myself. Another measure of distance is called the trace distance, and it's indeed a distance. It's derived from the trace norm. Trace norm is a trace of the absolute value of the operator or the square root of A star A. Okay, here's a dagger. So for Hermitian operator, if it has a spectral decomposition, so the trace norm is the sum of the absolute values of the eigenvalues. It is also unitary invariant because you do not change the eigenvalues under unitary transformation. And for two quantum states, rho and sigma, we define the trace distance as a trace norm of the difference. So this is a trace or norm one of the difference between rho and sigma. It can also be written as a maximum over all possible traces of lambda acting on the difference rho and sigma with a bounded operator lambda. It is indeed a distance, so it does satisfy the triangle inequality. And it also satisfies the data processing inequality, which is pretty cool, I think. But this is what we also expect from the measure of this distinguishability between quantum states, is that it gets harder to distinguish them when they pass through the noisy channel. So having those two measures, we're going to go back to them in a second. One way to generalize the quasi-relative entropy, well, there are many ways. Renyi entropy is one of the possibilities, and we've seen in the talk by Hanan yesterday, alpha Z relative entropy is another way, and here's another. This is a quasi-relative entropy, or f-divergence in this case. So for any operator monotone decreasing function or operator convex function that is 0 at 1, the f-divergence is defined as a trace of the function acting on the modular operator acting on rho. And the modular operator, it's a right and left multiplication. It's a product of the left multiplication by A and the right multiplication by the inverse. And if my states rho and sigma admit the following spectral decomposition with eigenvalues lambda and mu, and eigenvectors psi and phi, there is a closed form for the f-divergence, very easy to calculate. So it's lambda f acting on the fraction, and you have the overlap between the eigenvalues here. If you plug in here the log function, the negative log, that's an operator monotone decreasing function, the quasi-relative entropy becomes just a relative entropy. And if you take a function which is a power function, it's a operator convex function on 0, 2, that gives you the Tsallis Q entropy. And the Tsallis Q entropy is defined as trace rho to the power Q, sigma to the power 1 minus Q, with the normalization there. So the Tsallis entropy is used in different sides of entanglement, thermodynamics, statistics, optical lattice theory, and you can see more of the references in article on Scholarpedia titled Quantum Entropies that my student and I wrote. So if you take the power function without the normalization, it gives you, let's say, some alpha quasi-relative entropy, which is the basis for the Renyi relative entropy. The Renyi relative entropy, it has a log function after you take the trace. So it's not a direct partial case of the quasi-relative entropy, but it can be derived from there. And again, it's a very useful measure, Renyi relative entropy, that is used in hypothesis testing, entanglement-assisted conversion, and many, many others. And the capacity of quantum channels, that one of the, well, Wilde is going to be not talking about this today, but he has been working on that as well. Okay, so that's again, okay, here you go. The properties of the quasi-relative entropy are in a way similar to the relative entropy. It's invariant under unitary transformations. It's non-negative, and it is 0 if and only if the states are the same, which is really useful. And what's Path showed in 95 that it also satisfies the data processing inequality for completely positive trace preserving maps. So that this inequality deserves its own talk, and maybe if not the whole conference. So we will see more in the data processing inequality later today. So just a reminder, both of these measures satisfy the data processing inequality. And so the question is, how do we relate one to the other? A very famous inequality is called the Pinsker inequality, which relates the relative entropy with the trace distance. It's the relative entropy is lower bounded by the trace distance because, well, it can be infinite, and the trace distance is always bounded by 2. For quasi-relative entropy in 2016, here in Masoni, they showed a very similar, well, just a generalization of the Pinsker inequality with a prefactor of the second derivative of the function at 1. And if you plug in the minus log function, that's exactly what you get. You're going to get the Pinsker inequality back. So now the question is, can you reverse this inequality? Of course, with the different prefactors and stuff, but can you reverse this inequality? Can you upper bound the relative entropy with the trace distance? So that's a bit tricky because the relative entropy can be infinite. So you have to play around with the states. So the bound must depend on the structure of the states. In 2011, Odenberg and Izard, they showed the following reverse Pinsker inequality for the relative entropy. So here alpha is a minimal non-zero eigenvalue of the state, in this case sigma, and in this case it's rho. So alpha is a minimal eigenvalue. I'm going to use it throughout here. T here is the trace distance with a little bit like a normalization there to make it nicer. Now for Tsallis relative entropy, there's also been some work on the reverse Pinsker inequality. So if we denote lambda as the maximum eigenvalue and alpha as a minimum, here's what's been shown in 2011. It's upper bounded by 1 over q minus 1, and you have the maximum eigenvalue of rho divided by the minimum eigenvalue of both of the states. So this is for q between 1 and 2, and for q between 0 and 1, you get very similar, but here you can have, instead of the minimum eigenvalue of both, minimum eigenvalue of sigma. So it's a little bit sharper inequality. Okay, how do you generalize those two inequalities for the f-divergence? And here how I can do that. If you have two states, rho and sigma, they either two-dimensional qubit states or they're classical states. Okay, so these two cases. In those two cases, you have additional two cases. Rho is either full rank, or the function f is such that some coefficient is 0. I'm going to show in a second what that coefficient dependent on the function is. So just some special functions. Then the following holds. You can upper bound the f-divergence by the trace distance times the following expression. So here again, lambda is the largest eigenvalues, alpha are the minimal eigenvalues. And AF is a quantity that is derived from the function. I'll show where it comes from in a minute. Separately, if you just consider the relative entropy itself, then in any finite dimension, you can just upper bound it straight away by the maximum eigenvalue of rho divided by the minimum one times the trace distance. And for qubits, if you apply the previous theorem, that's going to give you a little bit sharper inequality because you're going to have here the minimum eigenvalue of sigma instead of the both of them. Okay, so before, just a reminder, this is what we had before. So of course, this upper bound is easier to compute. And it turns out that in any dimension, larger than 4, there are states for which the bound that I obtained over here is better than the previous one. For Tsallis relative entropy, the function, just the power function, when q is larger than 1, I cannot take that function because it's not operator monotone. But if you look at the original proof of Rostygin, that can be straight away improved without the constant. So you can get rid of this constant 1 over q minus 1, which is larger than 1 for q larger than 1. And if you apply the theorem that I showed you for quasi-relative entropies, then you can also get rid of this dimension of this prefactor 1 minus q. So previously, previously we had the same upper bounds, but with the prefactor depending on q, 1 minus q, which is larger than 1. So we can get rid of that prefactor as well.
Anna?
Yes.
I just have a small question. I hope I didn't mean to distract the description of this proof, but what is the main reason that one wants to sandwich the f-divergence between multiples of the trace norm? Is it because the trace norm is not actually a distance measure, and but while the trace norm is? Or are there other reasons?
Right. So what you're saying is what is the reason that we are looking at the reverse Pinsker inequality? Right. So the relative entropy. Well, one reason, yes, it's not a distance itself, like the trace distance is, but also it is interesting to see if the states are close when you measure by one measure. What can you say if you measure by another measure, right? So can you say something about that? I hope that makes sense. Yeah? Okay. So the idea of the proof that we rely on in this reverse Pinsker inequality research and the later one is the integral representation of the operator monotone decreasing functions. And that's a standard result in analysis, which was proved in 74. So this is the coefficient AF that I was talking about. That was one of the options for the function to have this coefficient to be 0. And here's the whole slide on all what of these coefficients mean, this b, and what is this mu, and how you calculate them. The point is that the log function has this coefficient 0, and the power function also has this coefficient 0. So if you want to consider those two functions, you're all good. So if you consider functions which are 0 at 1, the integral representation, you could get rid of this b additional constant there as well, and consider this difference. So the idea of the proof, if you look at the quasi-relative entropy, I can write it. This is the definition of the quasi-relative entropy, f of the modular operator applied to rho. But then I just add a 0, relative entropy of rho with rho. Yeah, so that's 0. And using the integral representation of the function f, I can write it as the integral, and here's the difference of the inverse operators. So here, I actually skipped a part where exactly you have to apply the fact that either AF is 0 or rho is full rank to get rid of that factor that you have before the integral. And then you just play around with this difference of the inverse operators. We're just trying to get the difference between rho and sigma over here. And if you calculate this whole expression, this whole expression, it's just some metrics applied to rho minus sigma. So this is exactly where we want to get our trace distance from. So if I want to look at the trace, one operator times another operator, I want to get my trace distance from here. So whatever this dt is, doesn't matter that much. So the lemma relies on the following. So let's say I have my matrix D in that form that I had previously. And then in two cases, when X is a diagonal matrix in any basis, or it's a 2 by 2 traceless matrix, like rho minus sigma is, then the absolute value of the trace of the product is less or equal than C, where C is the maximum constant over here in the matrix maximum entry there, times the trace norm of X. And if you apply that theorem, we already have this integral. You apply this upper bound to the trace, and you get exactly what we need to get. So we get the product of the t's, write it as a difference with the prefactor, and it turns out that that's actually my function f at the point alpha divided by lambda minus the constant at point AF, and just simplify it a little bit further. So the interesting question is, you can easily get the upper bound that depends on dimension because the absolute value of the trace of the product, well, that's the trace norm of the product, upper bounded by the trace norm of the product, which is upper bounded by trace norm of X times the infinite norm of D, or 2 norm of D, whatever. And from the structure of D, you can easily obtain the upper bound that's there, C times the square root of D. But can you get rid of this dimension? Because all the numerics that I and someone else did, we get the indication that there should not be any dimension dependent bound. And so the question, can we get rid of it mathematically? All right, and the second, quickly, I'm going to show you another problem, which is the closest separable state. So why are we looking at this problem? Let's say you have a bipartite state. It can be separable or it can be entangled. So if you want to calculate the amount of entanglement the state holds, how do you do that? Well, there are many ways to do that. For a pure state, if my rho is a pure state, then the entanglement is measured by the entanglement entropy. And that is sort of like a golden standard for entanglement measure. It's the entropy of the reduced state. And the reduced state is a partial, so this has to be B. So just where my hand is, that's a trace of the B, that's a partial trace of the pure state. And on pure state, it doesn't matter which partial trace you consider, on one state or the other, the eigenvalues are the same, and you get the same entanglement entropy. Now for mixed states, that's where it gets more complicated, because the marginal entropies are different, so I cannot take this definition anymore. And we need some other entanglement measure. Whatever measure you consider, it has to satisfy certain properties that we feel should be true. For example, it should vanish on product states. There's no entanglement there. It should be invariant under local unitary operations, and it should not increase under local operations in classical communications. You could also consider a few more additional requirements. For example, it could reduce to the entanglement entropy on pure states, but that is not absolutely necessary. So the relative entropy of entanglement, that's a measure of the entanglement on the mixed states, and it's calculated as the minimal distance between your state and a separable state. When I say distance, what's the distance? The distance is the relative entropy. So here we take the relative entropy as the distance between your state and any separable state. The minimal one is your entanglement. So you can take any other distance measure, right? So for any other distance measure, if you want to define an entanglement measure as the minimal distance, it has been shown in 90s that this distance should satisfy certain properties. For example, it should be 0 if and only if the states are the same. If you want your entanglement measure to be invariant under unitary operations, the distance should be invariant under unitary operations as well. And your distance should satisfy the data processing inequality if you want your entanglement to be non-increasing under LOCCs. So for relative entropy, if you take just like on the top of the screen over here, for the relative entropy, you can actually calculate for pure state what this closest separable state is. Not for any state, not for the mixed state. We still don't know for the mixed states what's going on there. But if you take a pure state, let's say psi, where's the coefficient square root pj? So pj is the probabilities here, and square root probability distribution amplitudes there. So the relative entropy of entanglement is the relative entropy between state psi and a separable state sigma of the following form. So the state sigma, it has the same probability coefficients and it's diagonal, well, it's more than diagonal in JJ basis. So if my state psi is here, the closest state is sigma psi when measured by the relative entropy. So again, just to point out, this is true only for pure states. We don't know what the closest state for mixed states are. And of course, what if I replace the relative entropy by the quasi-relative entropy? What's going on there? Well, there are several results here. For maximally entangled state, which has all equal probability distributions there, the quasi-relative entanglement is reached by the same state, sigma. And the same, I mean, the same state as is in previously. And the entanglement entropy, in this case, is a function at 0.1/d. Now, if you take just any pure state, the quasi-relative entropy for some large class of functions, I'll tell that in a second what that class is, but that class includes the negative log. Yeah, then it is reached again by the same state as it is for the relative entropy. And the expression becomes pj times f at point pj. So if you plug in minus log, that's exactly what you're going to get previously. Now for another sort of class of functions, if I don't want to restrict myself that much, I can consider another class of function. But that would only be true for qubit states. So if I have a qubit state in 0, 0, say 1, 1, then the quasi-relative entropy of entanglement, again, for some class of function that includes the power function, is the state of the form in the same sort of like basis 0, 0, and 1, 1. The Qs has to be calculated separately. It's a bit more complicated formula for the Qs. It depends on P, of course. And the expression for the entropy of entanglement is Pj times F at Qj. So what does it give us? For the entropy of entanglement, it gives us exactly the same result that we had before. So this is a true generalization. For the power function, from the power function, you can obtain either the Tsallis relative entropy or the Renyi relative entropy if you take the log afterwards. For the Tsallis relative entropy, the entanglement entropy of the maximal entanglement state is calculated as follows. D here is a dimension of your state, but it's interesting that it does not reduce to the entropy of the reduced states like it does for the relative entropies. So that would not be true in the Tsallis relative entropy case. For Renyi relative entropy case, you take the log after you calculate the quasi-relative entropy. And the entropy of entanglement is just log D for the maximal entanglement state. And it is actually does equal to the reduced entropy of the state. Okay, so how do you prove it? The idea is taking a derivative of a function. So we calculated the minimal, the optimization of the function, and what we have to do is to consider the directional derivatives. So if I consider the function f, which is a relative entropy between rho and almost the state that is the closest state. So this is the function in x that goes between the closest states, that's my guess, and any other state sigma. Then the goal is to prove that the derivative of this function at x equals 0 is non-negative. If we do that, then how do we show that that's the sigma star is the closest? Well, suppose that it's not the closest state, right? So right now I'm just trying to show why this is enough. If sigma star is not the closest, so there is a state, separable state sigma, that will have the relative entropy less than the relative entropy between rho and sigma star, then calculate this function f. This function f is the quasi-relative entropy just by definition. And if you calculate it, it's upper bounded by its convex in the second argument. So it's going to be 1 minus x times the relative entropy between rho and sigma star, and rho and sigma, forget about this, rho and sigma. So this is going to be 1 minus x times function f at 0 sigma and at 1 sigma. So there is no star here, my bad. And so what does that imply? This inequality would imply that if I calculated this difference, 1 over x between these two is less or equal than the difference between f1 sigma and, I have this Zoom stuff, and f0 sigma. So this will be negative, which is not true because the derivative is non-negative. Okay, so the point is that this is enough to prove. If we prove that the derivative is non-negative, then we're done. And to prove that the derivative is non-negative is very tedious calculations using the integral representations as well. The constraint on the functions that we're considering is the following. The function in P, which depend on f in the form of the measure. So if I take the same measure mu here as I take in my integral representation of the function and calculate this integral, that in the first theorem, the constraint was that's a constant function, because for log, that's just a constant function, or it is monotonically increasing or decreasing as 4-power functions. Okay, so the interest in future research is that can you generalize these results for any functions or for a larger class of functions? So if you have a pure state, can you say, or is it true that for a larger class of functions, the entanglement entropy is reached for a state of the following form, and it becomes just like in the last theorem there? All right, and I'm done. Thank you for your attention.